My name is Arun Raghunath. I'm a systems researcher at the labs in Intel. And my recent work has been in the area of distributed storage systems, data movement challenges in edge and cloud environments, looking specifically at visual and AI workloads. In today's talk, what I'd like to share with you is the work that we've done in accelerating storage accesses by decoupling the data path in SDS architectures. So I'll start by giving some context, some background about the space, and then I'll talk about the research approach that we have taken, and I'll describe a software proof of concept that we have implemented and some performance numbers on that proof of concept. All right, so with that, let me get started. So this is the background. So cloud storage services are popular, becoming used all over because they provide infinite scaling. They provide guarantees around high availability, durability, reliability, and this is offered internally by a cluster of servers that work together, where each server offers up its resources, like drives, for instance, to implement a given service. And the service is implemented by this middleware software layer, also called as a software-defined storage layer, which is running on each of these servers, and they collaborate with each other to provide the end-user visible storage service. So the picture there is basically showing a cloud block storage service provided by such an SDS middleware. And the point here that I wanted to talk about was client applications are basically connecting to a logical volume. And this logical volume is transparently sharded across the entire cluster. And the extents of these volumes are essentially stored on some subset of the servers within the cluster, right? And the middleware provides this view of a logical block image to the client application. So cloud storage has lots of desirable properties, but one of them which is not desirable is that its performance is actually quite slow. Compared to underlying hardware or the drives that are used, whose latencies are kind of in the microseconds, and you get millions of IOPs throughput, cloud storage services typically offer micro or millisecond latency and tens to hundreds of Ks of IOPs. So, and this is actually understandable if you think about the fact that the client application is connecting to a logical volume, and there's an SDS client-side library which needs to figure out, okay, where in the cluster should this request go, and when that request actually reaches the end storage server, there's another layer of translation that needs to happen, right? Because the client application is issuing IO requests to this logical volume, and there's a backing actual physical drive where the data of that logical extent is stored. So that translation needs to happen. So due to this going through this SDS software path, performance is lower than the actual hardware. We would like to have fast cloud storage. I mean, any storage service, we want it to be as performant as possible, obviously. But I think the point I'm trying to bring out in this slide is that there are many important usages where even if we can just speed up the read path, it would make a big difference. And so what I'm pointing out here is, there are lots of important usages like DL training, analytics, web search, which are read-only or read-heavy workloads, and they are over massive data sets. These usages are typically compute-intensive, so the jobs are scaled across many nodes, And so what you have is a huge data footprint, many nodes that are trying to access that data, and so you persist the data in cloud storage. And typically, because these usages are compute intensive, you end up renting instances in the cloud, which are expensive if you're renting a GPU instance or some accelerator. The worst thing that you'd want to have happen is your expensive compute resource is starved, waiting on data coming from a slow cloud storage service, right? And so today, the way folks deal with this is you prefetch the data subsets to local SSDs on the compute instance where your job is running. Couple of issues with this. This means you need to provision instances with local SSDs. That adds cost. You're also fetching and managing subsets of data over the entire massive data set that you want to work on, which adds complexity. The other approach is where folks either pay for a cache service, or you create and manage a custom distributed caching layer, essentially for the same reason, right? You load the data from your slow cloud storage service into a caching layer, which can feed your compute resources faster. So wouldn't it be nice if instead of all this cost and complexity, we have cloud storage which can give you near local drive performance, right? So that is kind of the context of the work that I'd like to discuss here. And our approach, the solution approach here was to look at decoupling the data path in SDS. So the question essentially was, can we completely bypass the SDS software stack for I/O requests? So the SDS software still will handle all the control functions, right? Like for a given extent or for a given object in the storage service, how many replicas, if it's replicated, or EC shards, et cetera, where that data should be, if a server goes down, who takes over, and all of that stuff will still be handled by the SDS middleware layer. But for the actual I/O, we want to basically avoid that bottleneck software path. And the basic idea here is, what if we have a companion module in the backend target storage server, which will take care of handling the I/O requests. So on the backend storage target server, the SDS stack can share the mappings of the data with this companion module. By mappings, I mean, for an extent in the logical volume, where is the actual physical drive and the offsets in the drive where that data resides, right? So if the SDS is aware that there's a companion module and it can share that, then this module can essentially cache that logical to physical mapping. And when it handles the I/O request, it can use that mapping and directly go to the drive and get the data. So in that way, we could kind of avoid going through the SDS stack for the I/O path. And again, would like to highlight that this sharing of the mappings will be under the control of the SDS stack, right? So yeah, I'll leave it there for now, and we'll talk more about that going forward. The other kind of interesting thing that we wanted to explore as part of this is, okay, we got a companion module. What if we can push that onto a hardware offload, right? And that way, it kind of gets interesting because now you're talking about a remote client getting to your media on the drive within the SDS cluster, all over a hardware path. And so that seems interesting, and that's what we were kind of looking at. So with those kind of goals in mind, we said, okay, we need to prove out whether something like this can actually work. And so we started looking at a software proof of concept to try out this idea. And again, I'll just get into some of the design goals that we had and some of the important points, if you will. So the first thing was, which SDS stack do we work with? We decided to use Ceph. It's open source. It's widely deployed in the industry. The other aspect is Ceph is quite complicated. It's got a whole bunch of modes and deployment options, and it actually offers all three storage interfaces, block, file, and object. And there are multiple levels of indirections and translations in Ceph itself. So the block-based logical volumes are actually created over objects. And the point of all of this is that it's complicated enough that if we can show that our proof of concept can work in Ceph, we think it lends credibility to the design, right? Like we can state that, hey, your favorite SDS stack could also kind of do something like this. So that was the first thing about choice, Ceph. The second thing is we're talking about the SDS layer kind of still managing the control plane and kind of sharing these mappings with a distinct module, right? So for something like this to work, you have to make sure that this companion module is always in sync with the SDS. So if for whatever reason the underlying data for a given logical extent or a given object is moved, then if the SDS has already shared the mapping for the previous location of that object, it better be able to yank it out from the companion module. So with that in mind, we devised a protocol to share mappings and a protocol that allows the SDS to essentially evict any mappings it has shared before whenever it wants, right? There's also another aspect of it wherein if the companion module runs out of cache space, it can report to the SDS that, hey, you've given me this mapping, I no longer have space for this, so I'm going to drop it, just letting you know that, right? So that aspect of the communication is also possible. And we modeled this protocol on the PCIe address translation services, again, with an eye towards future hardware IP, if we can push this direction further. Yeah, I think that was about the making sure that the SDS layer is in kind of sync with the companion module. And I've had a couple of folks scratch their heads about why PCIe ATS here. There's a parallel here. If you think about it, the ATS is for devices which are looking for the virtual memory address and its translation. And here we're kind of in the same space in the storage domain. We're looking at virtual extents on a logical a block device, if you will, and the corresponding mappings of that, right? So that's where, why we went down this path. Okay, the third point was around the memory footprint. Again, if we want to have a companion module like this run on a hardware accelerator, it cannot have a really big memory footprint, right? So, because memory is typically a scarce resource. So we actually started with a compression-based approach, trying to fit all the mappings into memory, but that we moved off of that design, and the design has now evolved to a cache. Essentially, it's a mappings cache, and a subset of the overall logical to physical mappings are held in this companion module. And we think that gives us kind of the sweet spot of being able to do a direct path and being able to keep in sync with the SDS, where it can yank the mappings as it needs. And finally, I mean, the goal with this software proof of concept was to characterize and understand the interactions between the cluster level operations and the I/O requests and the I/O data path, basically. So identifying bottleneck paths between an offload and a SDS running on a host CPU, and interface recommendations not only for the offload, but also for the SDS, right? If what are the architecture changes or interfaces that you would like to expose in the SDS if you knew that you have an offload which can take care of the data path. Yeah, so this is about the design goals. I'll now click down to the next level where, like I said, we started with Ceph. And so I'll just talk about where we went with this. So in Ceph, client applications essentially get to the storage server service. In this case, the picture is basically showing a block service via a client-side library, which, it's librd Rados Block Device, which essentially takes care of communicating with the Ceph backend using a custom protocol called Rados. Now, the Ceph community already has started doing work to enable NVMe over Fabrics paths into Ceph. It's called the Ceph Gateway Project. And their goals here were to enable bare metal clients to be able to connect to Ceph. The idea being that if you either don't want to or cannot basically install Ceph-side libraries in your client VM image, for instance, you should still be able to use Ceph, right? So that was kind of the goal of this gateway project. And the way they've kind of done this is the client application can talk NVMe or Fabrics. It connects to a Ceph gateway, and that gateway essentially does the translation to the custom Ceph protocol, i.e. Rados. The other benefit they get is it reduces the client-side CPU overheads because they don't have to run the librd there. But nowhere in this work is performance looked at. Right? Again, NVMe drives can operate in tens of microseconds, remote access over NVMe or Fabrics in tens to hundreds of microseconds. But the goal of this work was to maintain the default baseline performance, which is over Rados, right? So that's where our work kind of starts, where we say, okay, let's look at separating the control and data paths. And the first thing here is we want to extend the NVMe over Fabrics path from the client all the way to the backend server where the Ceph OSD is running, right? This means on the initiator side, we need some way to locate the server in the cluster, which is responsible for the specific extent that's being accessed in this I/O request that the client's trying to send. Now, the nice thing here is there's already standardization work ongoing in the NVMe twigs. So ADNN, Adaptive Distributed NVMe over Fabrics namespaces, it's a mouthful. But they are looking at exactly this problem, how using NVMe or Fabrics, you can get to the correct owner, if you will, of a particular extent in a distributed environment. So that part is kind of already taken care of, if you will. And just by way of context, I also wanted to add that a few tier 1 CSPs have also done or taken a similar approach in terms of sharing sufficient state from their backend storage service to the client side so that the client can directly get to the backend storage service. But these are all kind of custom and they are out-of-band mechanisms versus the NVMe over Fabrics is kind of as part of the standards, right? So we've gone with, for our software proof of concept, using ADNN. So that gets us from the client to the backend storage server, but we want to go all the way to the drive, right? Because if you just get there and then throw it back to the SDS stack, then you incur the same overheads again. So that's not where we want to land. And so that is the focus of the software proof of concept. What is the target data path, or the data path within the target server, which will allow us to do this end-to-end from a remote client over NVMe or Fabrics to the drive within a Ceph cluster. Okay, so now this is a picture of the modules or the components inside the storage target server where Ceph is running. And I'll talk about what changes we did or what we've added here. So on the top, in Ceph itself, we've added some patches to share the logical to physical mapping. So Ceph has actually got a layer called Blue Store, which essentially takes care of all the block mappings, and it handles all of that internally. So the patches that we've added essentially allows us to get that translation. So given an object and offset and length in that object, where on the actual physical drive that the Ceph OSD/Blue Store is managing is the data for that object stored. So that patch will essentially allow us to answer if someone asks us the question, us meaning us, the Ceph OSD, tell me where this object is on the actual physical drive. The second part is the companion module. So this is, we've implemented this in SPDK. So it's an SPDK application. And I've just kind of shown the 4 main modules here. We've taken advantage of some of the stock modules available already. The NVMe-over Fabrics target is well implemented and understood in SPDK already, as well the AIO BDev, which is an async IO block device, which allows this user space application to access a Linux kernel block driver. So those 2 parts kind of we just leveraged. But now on to the parts that we implemented. So I'll kind of explain that as part of an IO flow. So you get a block request. It's terminated in the NVMe-over Fabrics target module. And that hands it off to the block device that's responsible for the namespace which this IO request comes in for. This, we call it the fastpath BDev. So this BDev essentially maintains that cache of mappings, right? So it will check that, okay, do I have a mapping for this extent which is being requested in this IO request? And let's say it doesn't have it. Then it turns up, and that's our miss path, right? So it will say to the translation service above that, hey, I need a mapping for this extent. Can you get it for me? The reason we need to have this translation service is because, like I mentioned before, Ceph OSD, the object storage daemon, works with objects. And basically a block image, the logical block image that a client is issuing IO requests to are actually backed by underlying Ceph objects, right? So the Ceph OSD patches that we've added, it just talks objects. So we need to do that translation from the block image and extent to the corresponding object, which is backing this. Thankfully, this is algorithmic, right? So in the sense that there's a simple, well, I shouldn't say simple, but there is a well-known algorithm where given a particular extent and an RBD image, which is Ceph terminology for logical volume, you can translate to the actual object that is backing it, the name of the object, I mean. So we've essentially pulled out that code from the Ceph OSD and put it in our translation service here. So that guy converts from the block request to the corresponding object and sends that request to the Ceph OSD. And with the patches I mentioned before, we'll get the mapping back. So the translation service then answers back to the fastpath BDEV that, okay, here's where on the drive the actual data for this object is present. So the fastpath BDEV will now cache this mapping. Now, when you get another block request for that same extent, the fastpath BDEV consults its cache, and it knows what actual drive location to issue the IO request to. And so that is our hit path. It goes, it sends that request to the AIO BDEV, which will then get that correct data from the drive, which is actually being managed by the Ceph OSD. And so that's kind of the what we've done in this software proof of concept. What else? Yeah, I think this was kind of the main part that I wanted to describe in the software proof of concept. Okay, so next is basically, okay, let's see if it works. And this was our experimental setup. It's a simple 2-node Ceph deployment. Each node has one OSD managing one NVMe drive. Prior to our test runs, we use FIO to write a large RBD image onto this drive. Ceph allows you to only fill up to 85% capacity of a given drive, and beyond that, it goes into fail-safe mode. So that was the extent that we could write on the drive that we had. So it's a 600 GB RBD image that we have written random data with, and the test run will be 1 million random reads of small 4 kilobyte size requests. In the experimental setup, I also wanted to point out that on the client node, we are using FIO, and there are two engines. There's the RBD engine, which is the default Ceph library that will be used, and the other is the NVMe-over Fabrics initiator. And we also added a gateway node here so as to be able to compare our performance with the Ceph gateway work. Yeah, so this is our experimental setup. And in terms of the IO paths that we're going to measure, it's the baseline where the client is sending the custom Ceph protocol that is Rados requests. The next IO path is through the NVMe-over Fabrics gateway. So from the client, you get an NVMe-over Fabrics request converted to Rados request by the gateway. The third one is where we got a miss in our fast path. So this is where now on the gateway, we're using the ADNN module, this guy here. So what's coming out of the gateway is still NVMe-over Fabrics now. And then the miss path that I described in the previous slide. And lastly, it is, you got a hit in your mappings cache. And so you're able to read directly from the drive. So here are the results that we got. So random read latencies, 1 million reads of a small 4 kilobyte size each over a 600 GB RBD image with a queue depth of 1. That's kind of the hardest thing in the sense that there's no parallelism to exploit. There's just one IO request. What's your latency, right? So that's what we wanted to measure. On the y-axis, it's the completion latency in microseconds. And I want to point out this is a log scale. On the x-axis, the completion latency, we have average and the different percentile latencies. So if you just focus on the leftmost set of 4 bars, the baseline is default Ceph using Rados. So that comes up around 1 millisecond. The IO path through the Ceph gateway is thereabouts. It's a little lower, but it's in the same ballpark. And the fast path miss adds a little bit of latency to that. But what's interesting is the fast path hit. It's 120 microseconds instead of 1 millisecond, right? And so that's kind of what we were shooting for, right? The hardware path that just bypasses the entire SDS stack. And this trend you can kind of see across the different percentile latencies here. The black line is actually showing how good one could get in software, right? So there we've done local drive. So on the backend storage target, if you had FIO running right there and accessing through software the drive, what would the latency be? It's around 80 microseconds. So we are kind of close, which was encouraging, right? So I think a couple of points to just highlight here. I want to make sure it's clear that even when we do the hit path, there's no data being cached. We are reading the data from the drive. What's being cached is the mapping of, for this logical extent, where is the actual physical extent. So that's what the fast path hit is measuring. And in our POC, we are getting an order of magnitude reduction in latency. So that previous one was for queue depth 1. This one is showing throughput, where we vary the queue depths from 1 to 128. And I mean, for simplicity, we just shown the baseline and the fast path hits. And you can kind of see a similar trend here. It's a 4 to 10x increase in throughput across the varying queue depths. So even as you increase the load, we're seeing good performance speedups here. Yeah, so this is basically what I wanted to share. To summarize, we wanted to see if we can decouple the data path within the SDS architecture, where the SDS stack continues to do all the cluster level operations, provides all the usual SDS guarantees, but we have this companion module where we can basically get a direct path to the drive. I should say that the proof of concept so far, we've only looked at the read paths. We haven't gone to writes, which will get a little more complicated. But I think the point I wanted to make was, even if we can do just this, even the reads, there are lots of important usages where we think this will be valuable. Wanted to again reiterate that the SDS is in control of the mappings. It can evict them at any point, so we can make sure that the offload and the SDS stay in sync. And we've implemented this proof of concept in Ceph, showing an order of magnitude improvement. And there's ongoing work where we are trying to test this proof of concept at scale, increase the number of OSDs, drives, logical volumes, and clients that are kind of using this. And we're also looking to see if we can expand beyond block storage to object and file as well. Now, that will probably get us into a space where we'll have to do some custom extensions. We can't just rely on the standardized NVMe-over Fabrics, obviously. But again, if we can get significant speedups, we think it'll be well worth going down that path. And lastly, we want to try, what I shared so far was all a software proof of concept. We want to see how much further we can go if we can move this companion module onto a hardware accelerator like a sNIC, IPU, what have you. And so, yeah, basically the goal here is to see, can we get all the guarantees and the nice properties of cloud storage, but maintain near local drive performance. So yeah, that's my talk. Thanks. And yeah, I look forward to any questions, comments, feedback. Sure.
Go to the histogram slide. Can you go to the histogram slide? So it looks like the fast path, the tail is getting worse. And you can see even your baseline, it gets a little bit worse, but why is the fast path growing? Like the tail looks like it's growing.
Yeah, this is a question everyone who sees this kind of asks this, and I think it's basically.
Excuse me, what was the question?
Thank you. So the question here is that if you look at this graph, as you go to the the 4 nines percentile latency, you can see that the fast path latency is kind of shooting up from the 120s thereabouts to almost 2 milliseconds, right? So the question was, what gives? Why is that the case? I think the only answer I have to that is, even if you look at the local drive, the black line, right? That is also kind of shooting up quite a lot. It goes up to from 80 to 212 mics, right? And yeah, I don't have a better explanation other than to say, hey, even when I'm doing local, I'm seeing that same behavior. It's about how the drive is getting hit, and the 4 nines latency on that.
So you think it's the hardware itself, the SSD or HDD, whatever.
Right. That's my only explanation for that at the moment. Yeah. Right. Yeah, the 4 nines tail latency is kind of really shooting up. Actually, the person in the back. Yeah, go ahead.
Yeah, just a brief question. So I think I understand the concept, but what happens if there are data services sitting on the hot data path? Because Ceph also has encryption and it has erasure coding.
So the question was, here you're showing just the basic read performance, but Ceph also has other data services like encryption and compression, and what happens if you add those on top of this, right? Actually, great point, and this is not something we've got performance numbers on yet, but I think this is exactly why the hardware offload path is super interesting, because for example, on the Intel IPUs, we have hardware IP blocks that can kind of manage this, compression, etc., in hardware, and so we think that the benefits when you add those data services on top of this would be even better. Maybe not in terms of actual, well, Ceph does it all in software, so we will see significant improvements over that, but also in terms of reduced CPU usage on the backend hardware where you're running the OSD is another gain that we expect to get. So actually, this is something I didn't talk about, but the other nice thing here is, if for the IO path you can do this kind of a bypass, forget the performance angle. If you look at it from a TCO angle, right? The way Ceph servers are provisioned today, it's with the goal of, okay, I have this amount of CPU resources, and I have this kind of performance I want to meet. And based on that, you provision the number of OSDs that will run on a given server and the number of overall servers that you have. If we are able to take all the I/O load away and thereby reduce CPU usage significantly, we think there's also a good TCO angle here. Like, the same hardware can actually probably give you a lot more, right? So this is just turning the argument and seeing the benefit from a different lens. So, yeah. Hey, there was a question here as well.
Yeah, back to the fast path. You said there was a cache in there in the event that you did not meet, if you actually found the consolidated address earlier. How big is that, and does that play a role in any of this latency that you're seeing? The fact that it's not sized perhaps sufficiently, you have to go.
Okay. So the question was, you mentioned that there's a cache in the companion module, and the question was around what is the size of the cache, and whether it's not correctly sized, and therefore you're seeing the high tail latency, right? The cache, so I did play around with increasing the cache size significantly, and that I don't think will explain the tail latency that you see there. So the cache itself is, so this the implementation is a lockless multi-threaded implementation where we don't expect to see non-linear kind of latency increases because of locks being held, etc. It's completely lockless, and by way of size, at least as a rule of thumb, what we calculated is for a terabyte of actual drives space that you are wanting to kind of have this fast path for, you need about a gigabyte. So it's 3 orders of magnitude lesser. And there are lots of knobs there that we can play with, because essentially that entry in the cache is a logical to physical translation, right? So we have knobs where we can essentially say what is the size of an extent in Blue Store. Like when it is doing its block layer management, there is a knob there which allows you to say, hey, the smallest size that I will manage is, blah, right? So it's 128K or 1 meg or whatever. So we can actually play with that and add entries in our cache for larger block extents and thereby kind of, get this fit. So, yeah. So I think in summary, the mappings cache is a lot smaller, and I don't, at least in the experiments I've done so far, see that as being the reason for the spike in tail latency. All right, I think no more questions.
Could you go to slide 5, I think it is?
Go to slide 5. Okay. Oh, here. Okay.
Yeah, so somewhere on there, you started looking at a compression-based
Oh,
algorithm, and then
right, switched over.
probably the overhead, I should imagine, is quite high. Is there a hybrid approach there, potentially?
Fair point. So the question is
Down on
both, right? So yeah, the question is in the third bullet here, we're talking about starting with a compression-based approach, from which we switch to a mapping table cache, and does it have to be one or the other? Can you have a hybrid of both? Is essentially the question. So let me start with why we did the switch. So when we were starting with the compression-based approach, we actually started off with the hope that for the entire available extents on the drive, can we compress and get all the mappings into a small amount of DRAM available on a hardware offload? And that started getting increasingly challenging because it's not just one drive, right? We want to have 16, 20 more drives. And there was just no way we were going to get this to fit. And so that's where we switched over and said, okay, we can't do everything. But do we even need to do everything? Because it's not that all those drives and all those extents are getting accessed at the same time. And so that's where we switched to the cache-based approach. Now, in terms of can you compress that as well? Potentially. But I mean, if you look at the data structures, they're really small. I mean, it's literally the logical extents and the physical extent. That's it, right? That's all there is. So, I mean, you could, in theory, compress that some, but you will pay the cost of decompressing it and all that. Now, one other vector that we have discussed, but not actually implemented anything, is if you have a hardware offload with limited amount of DRAM, you get a miss here, and when you go to the host CPU where the SDS stack is running, we could still have a companion module there as well. So there, that would be exactly like what this software proof of concept is. You have the SDS, and you have a companion module that's caching. Now we can take advantage of the host DRAM and have a bunch of mappings cached there. So a miss from the hardware can still be a hit in the host DRAM, which is a larger memory, which has a larger footprint. And so we've kind of looked at that. We've looked at talked about, not actually implemented anything yet. We've talked about, hey, what if we have CXL attached memory? You know, we could actually kind of have other tiers here and take advantage of that. It comes with the caveat of being extra careful of when you're evicting, you better make sure everything is in sync or your host, right? So, yeah, that's, okay, a question here.
Can we quantify how much performance gains are we getting just because of caching and just because of decoupling the whole data path?
Well, so the question was, can you quantify whether the benefits that you're seeing, how much of it is from caching and how much is it from decoupling? I mean, we're able to decouple only because we have cached the mapping, right? So what is decoupling? I got the mapping, and so I can go directly. Maybe you're asking about the protocols, different protocols? No, okay.
I can reframe my question.
Sure.
If we were not to decouple it completely, but the Ceph were to implement the caching inside itself.
Okay, fair point. Yes. So actually, the follow-on there was to say, why decouple from the SDS software application, if you will, have the cache inside it itself, and why create a companion module, right? That's, I think, where you're going with that question. And that's a fair or a very good observation. When I presented this to the Ceph community, that was the first thing they said. They were like, hey, this is all very nice, but we can do this inside our software stack and get all these benefits, so why wouldn't we do that? The only kind of answer, it's not really an answer, that can absolutely be done, and that is of high interest in the Ceph community. So what they told me was, come back with the interfaces between an offload and the, the Blue Store layer that you have, and then we'll talk again, because we would want to implement this inside the Ceph stack itself. My only counter there is to say that, hey, if you want an end-to-end hardware path, then being able to do this in a companion module is kind of beneficial, right? Because that's when you can actually put it on a separate hardware accelerator. And that was one of our goals from the get-go, and which is why we went down this path. But absolutely fair point. You could do this inside. I would expect to get the same kind of performance gains if you implement it, because that's what I've done. It's all in software at the moment. If we push it to hardware, we can probably get more performance gains and save CPU cycles on the host CPU, which gives you the TCO angle that I spoke about. So, hope that answers your question. Okay. All right. Thanks all. Thanks for the question.